Hi folks, in this video I'm going to talk about the fundamental theorem of calculus, which has two parts. But before I talk about this specifically, I'm going to talk about the relationship between areas and antiderivatives. And after we see the fundamental theorem of calculus and several examples, we are going to discuss the net change theorem, which is actually a topic from section 5.4 of the textbook. So section 5.4 talks about indefinite integrals and the net change theorem, but we have already discussed indefinite integrals when we talked about antiderivatives in section 4.9. The fundamental theorem of calculus relates finding areas and antiderivatives, and like I said, it has two parts. In the first part, we are going to see that there is a relationship between an indefinite integral and giving all the possible antiderivatives of a function. And in the second part, we're going to see that if we have a definite integral, that is the same thing as evaluating assigned area between the graph of the function and the portion of the horizontal axis from A to B. Let's take a look at this example. Let little f of x be equal to x plus 1, so it's the blue line here in this graph. And for any x, capital F of x is going to denote the area of the region between the graph of f and the portion of the horizontal axis from 0 to x. So if we want to evaluate this area, let's call this A1 and A2. So f of x is going to be A1 plus A2. So it's the area of a triangle and the area of a rectangle. So this point here is the point 0, 1. This point here is the point x1. And this point here, it's already marked. It's the point x plus 1. So the area of the rectangle is the triangle first. So the area of the triangle is going to be the base, which is x, times the height, which is x plus 1 minus 1, so x, and we divide this by 2. And the area of the rectangle, so the height is 1, and the base measures x, so we can simply write this as x squared over 2 plus x. So this is going to give us capital F of x, which is what we have here. And let's notice that if we differentiate capital F of x, let's do this using the power rule. This is going to be half times 2x plus 1, which implies that f prime of x is x plus 1. So notice that the derivative of capital F of x is x plus 1, and the function that we had represented in blue by little f of x is also equal to x plus 1. So what is interesting about this capital F of x, this function capital F of x, is that the derivative is going to be equal to x plus 1, which was little f of x. So uh, this example doesn't show for every situation, for every function, that this is going to be the case, but it turns out that it's going to be true. So let's say this another way. An area function is an antiderivative. So this is always going to be the case. So as in our example, little f was a continuous function and a was any real number. Then we're going to define capital F by letting capital F of x be the signed area of the region between the graph of f and the x-axis from a to x. Then capital F is going to be an antiderivative of little f. So in other words, f prime of x is going to be equal to little f of x. Now we are ready to talk about the first part of the fundamental theorem of calculus. And as in our previous example, we are going to let f be the area function. Then we can express this area function using the definite integral. So integral from a to b of f of x dx. And this is going to give the area of the region between the graph of f and the x-axis in the interval from a to b. In this case, we say that the letter x acts as a dummy variable. It means that we can change by any other letter, by any other variable. and it's not going to change the meaning of the expression. So because we want to express the area function, the area as a function, and we usually use x for functions, we are going to use a different variable, say t, to express the area function, capital F of x, as the integral from a to x of f of t dt. And the reason we do this is because replacing x by t is going to free up the letter x to be used as an upper limit of integration. We saw that capital F was an antiderivative of little f, and it was also an area function. So we have f prime of x is equal to little f of x, and capital F of x is the integral from a to x of f of t dt. And then we can combine those two pieces of information and use Leibniz notation to represent that the derivative with respect to x of capital F of x, which is this integral that we have here, is going to be f of x. And this is the statement of the first part of the fundamental theorem of calculus. So if we have an integral from a number a to x of a function, continuous function f of t dt, then the derivative of this integral with respect to x is going to be little f of x. Let's see a few examples of how to use the first part of the fundamental theorem of calculus. Let's start with this example where I have to evaluate the derivative of this integral. So I'm going to start by letting f of t be arctangent of t cubed plus t squared plus t plus 1. Then I'm going to rewrite d dx of the integral from 2 to x of this function. This is simply going to be equal to d dx of the integral from 2 to x of f of t dt. And that is by the first part of the fundamental theorem of calculus, that is equal to f of x, but little f uh, was given up here. So this is going to be arctangent of x cubed plus x squared plus x plus 1, which is exactly what we have here. Now, in this example, we are evaluating the derivative, but the lower bound is x and the upper bound is 0. So the statement of the first part of the fundamental theorem of calculus says that my upper bound has to be equal to x and my lower bound can be any real number. So I'm going to use a property of integrals to rewrite this integral as follows. This is the same thing, dx of minus integral from 0 to x of cosine of t over t dt. And I can take this minus sign outside. I'm going to place it here. So let me erase here. Now I know how to apply the first parts of the fundamental theorem of calculus to solve this. So this is going to be minus cosine of x over x. In this example, we have to evaluate the derivative of this integral, and the lower bound is a number, but instead of the upper bound being x, we have x squared plus 1. So we don't know how to use initially the first part of the FTC to solve this derivative. But if we had h of x as being the integral from 1 to x of e raised to t over square root of sine of t plus 1 dt, then to this function, we would know how to apply first part of the FTC. So it turns out that if we evaluate h of x squared plus 2 plus 1, sorry, this is going to be the integral from 1 to x squared plus 1 of e to the t over square root of sine of t plus 1 dt. And now if we differentiate the left-hand side and the right-hand side with respect to x, this is going to give us d dx of h of x squared plus 1 equals d dx of the integral, which is the integral that we were originally given to differentiate. So we do know how to differentiate the term on the left-hand side. We have a composition of functions. This means we have to use the chain rule. So let me diminish the size here. So applying the chain rule on the left-hand side, it's going to give us d over dx of h of x squared plus 1. That is equal to the derivative of the outer function evaluated at the inner function times the derivative of the inner function. The inner function is x squared plus 1, so its derivative is equal to 2x. Now, I do know how to evaluate h prime because h of x is given by that integral, and I can apply um, the first part of the FTC to that integral. So this is going to give uh, e to the x. It would give e to the x, but we are evaluating at x squared plus 1. So e to x squared plus 1 over um, sine of x squared plus 1. And then we take the square root of that. And we multiply by 2x. We have the first part here and the conclusion here. In this example, both the lower bound and the upper bound are functions of x. So what I'm going to do is I'm going to rewrite this derivative as d dx of integral from x squared to 0 of e raised to minus t squared dt plus the integral from 0 to x cubed of e to minus t squared dt. So I'm using a property of integrals here. Now, in the first integral, the lower bound is a function of x, and it should be a number. So I'm going to rewrite as follows. This is going to be d dx of minus 0 to x squared e to minus t squared dt. Once again, I'm using properties of integrals plus 0 to x cubed times integral of 0 to x cubed of e to minus t squared dt. So now I'm going to call my function h of x equals the integral from 0 to x of e to minus t squared dt, and plug in that um, into here. This gives me d dx of, now on the left, for the term on the left, I'm going to have minus h of x squared, and for the term on the right, I'm going to have h of x cubed. So because this is a composition of functions, I don't know how to use the chain rule to differentiate this. So this is going to give me minus h prime of x squared times the derivative of the inner function, which is x squared, so the derivative is 2x, plus h prime evaluated at the inner function times the derivative of the inner function, So derivative of x cubed is 3x squared. So I do know how to evaluate the derivative of h using the first part of the FTC. So this is going to be minus e raised to minus x squared times 2x plus e to minus x cubed squared times 3x squared. And we have the first part of the solution here. If you need this slide to make observations, you can use. And the conclusion is right here. The first part of the FTC tells us that there is a relationship between areas, antiderivatives, and integrals. And the second part, which we are going to introduce now, is going to tell us a simple way to evaluate definite integrals. So let g of x be defined as the integral from a to x of f of t dt. Then this means that g is going to give us the area between the graph of f and the x-axis from a to x. If f, capital F, is any other antiderivative of little f, then we know that uh, g of x is going to be equal to f of x plus c, because any two antiderivatives, they differ only by a constant. I left this slide blank if you want to make observations about what I'm going to show next. The second part of the FTC tells us that if we want to evaluate a definite integral from a to b of f of x dx, then we can start by replacing our variable x by a dummy variable t. And then we are going to be able to rewrite this integral as the integral from a to b of f of t dt, which is exactly what we have up here, minus the integral from a to a of f of t dt. And this is true because one of the properties of integrals tells me that if our lower bound is equal to our upper bound, then this integral is equal to 0. Let me remind you that in the previous slide, we defined g of x to be the integral from a to x of f of t dt. So this means that this first integral here is g evaluated at b, which is what we have here. And the second term is g evaluated at a, which is what we have here. Then if f is any other antiderivative for little f, g and f are going to differ by a constant. So I can say that g of b is the same thing as f of b plus a constant c, and g of a is going to be f of a plus a constant c. So this c is going to cancel with this c. And finally, the integral that we were given in the beginning is the same thing as f evaluated at b minus f evaluated at a. We usually abbreviate f of b minus f of a, writing f of x with a bar and then a b up here and an a down here. This is exactly the statement of the second part of the FTC. So if we have a function little f, and if we integrate from a to b, this is the same thing as obtaining an antiderivative capital F and evaluating at the upper bound and at the lower bound and subtracting those two numbers. Let's see how we can use this second part of the FTC to solve some problems. So you may remember this example from last time where we wanted to evaluate the integral of f of x squared dx from 0 to 1. Now we are going to evaluate from 0 to 2. And it took us a long time to solve this. We used uh, addition of areas of rectangles, and then we used sigma notation, which was very complicated because then we needed to take a derivative as n went to infinity. So this was way too much work. What the second part of the FTC is going to tell us is that there is a nice way for us to evaluate this integral. By the second part of the FTC, this is equal to x cubed over 3. So x cubed over 3 is an antiderivative for x squared. And then we put a bar here, 0 and 2, which are the lower and upper bound. So we evaluate at 2, so 2 cubed over 3 minus, now we evaluate the function at 0, the antiderivative at 0. So this is going to give us 8 over 3. So we could solve this problem in one line while it took a very, very long time to solve it using the previous technique. And here's the solution typed. Now to evaluate this, we are going to start by finding an antiderivative for this function. So antiderivative of x squared is x cubed over 3. The second term here is the same thing as x raised to half. So we can use also the kind of an inverse of the power rule. So this is going to give us x raised to 3 over 2 divided by 3 over 2, which is the same thing as multiplying by 2 over 3. And antiderivative for minus 1 is x. Now we evaluate all of this at the lower bound and at the upper bound. So plugging 1 here gives us 1 over 3 plus 2 over 3 minus 1. And now we have to subtract um, from the antiderivative evaluated at 0. But when we plug 0 here, the first, second, and third term are going to be equal to 0. So this is going to be uh, 3 over 3 minus 1. So this is going to be equal to 0. To evaluate this integral using the second part of the FTC, we need to know antiderivatives for those two terms. We know that an antiderivative for secant tangent is secant, and an antiderivative for secant squared is tangent. So this integral is going to be equal to secant of x plus tangent of x, evaluated at the lower bound and at the upper bound. So by definition, secant is 1 over cosine of x, and tangent is sine of x over cosine of x. And we are going to evaluate at the lower bound and at the upper bound. So let's make those evaluations. This is going to be 1 over cosine of 2 pi over 3, which is minus half, plus sine of 2 pi over 3, square root of 3 over 2, and then cosine of 2 pi over 3 minus half again, minus the function, the antiderivative evaluated at the lower bound. So this is going to be 1 over cosine of pi over 3, which is half, plus square root of 3 over 2, which is sine of pi over 3, over cosine of pi over 3, which is, once again, half. And making these evaluations, we see that this is going to give, let's see, if we add this number with this, it's going to give minus 4. And then if we add this with that, it's going to give minus 2 square root of 3. And that is what we have here. Let's take a look at one more example. Here we have to evaluate this integral, but we do not know an antiderivative for the integrand. So we are going to use a technique called substitution. I'm going to call u equals cosine of t plus 1. Then the u is going to be minus sine of t dt. Now, those values here, the lower bound and the upper bound, they mean that the variable t is equal to them. So when t is equal to pi, this is going to imply that u is going to be cosine of pi plus 1, but cosine of pi is minus 1, so this will be minus 1 plus 1, which is 0. And when t is equal to 3 pi over 2, u is going to be equal to cosine of 3 pi over 2 plus 1. And because cosine of 3 pi over 2 is 0, this is going to be 1. So we can rewrite the integral that was given to us as the integral from 0 to 1. So when t is equal to pi, u is going to be 0, and when t is equal to 3 pi over 2, u is going to be 1. Then here we have the cubic root of cosine of t plus 1, but cosine of t plus 1 is u. So this is going to be the cubic root of u, or u raised to 1 over 3. And then we have a sine of t dt here, but we do have that minus sine of t dt is equal to du. So this is going to be du, and then the minus sign I'm going to put in front. Now I do know how to integrate this function by using the reverse of the power rule. So this is going to be u raised to 1 over 3 plus 1, which is 4 over 3. And then we divide by 4 over 3. That is the same thing as multiplying by 3 over 4. And now we have to evaluate at 0 and also at 1. When u is equal to 0, this is going to give 0. So we just have to evaluate when u is equal to 1. When u is equal to 1, 1 raised to 4 over 3 is going to be 1. So this is going to be minus 3 over 4. If this example was a little bit hard to follow, don't worry, there are plenty of examples in section 5.5. I already completed this, so here's the final answer, minus 3 over 4. Now let's talk about the net change theorem, which is just another way of putting the second part of the FTC. So the second part of the FTC tells us that if we have a continuous function on an interval, closed interval from a to b, then the integral of this function is going to be f of b minus f of a, where capital F is an antiderivative for little f. If capital F is an antiderivative for little f, we can rewrite the expression that we have above, the equation that we have above, by putting the integral from a to b of capital F prime of x dx is equal to f of b minus f of a. And this is exactly what the net change theorem says, because capital F prime is a rate of change. Then another way of putting the second part of the FTC is saying that the integral of a rate of change is the net change. So the function, the antiderivative evaluated at the endpoint minus the antiderivative evaluated at the initial point. Let's use this information to solve this problem. A particle moves along a line so that its velocity at time t is given by this function, and we're measuring in meters per second. We have to find the displacement of the particle during the time period from 1 to 4 seconds. So the displacement is the position of the particle at the end minus the position of the particle at the beginning of the time period that we are considering. And this is the same thing as the integral of v of t dt. So remember that velocity is the derivative of position. So position is going to be the integral of velocity. And our lower bound is going to be 1. Our upper bound is going to be 4. So this is going to be the integral from 1 to 4 of t squared minus t minus 6 dt. And now we know that if we come up with an antiderivative for this function in the integrand, we just have to plug 1 and 4, evaluate and subtract. So this is a polynomial function. We know how to integrate polynomials. So this is t cubed over 3 minus t squared over 2 minus 6t. And then we evaluate at 1 and we evaluate at 4 as well. Then plugging 4, this is going to be 64 over 3 minus 16 over 2 minus 24. Now we subtract from the function evaluated at 1. So this is going to be 1 over 3 minus 1 over 2 minus 6. And then the answer to that you can see in this slide, which is actually a negative number. So you may be wondering, if an integral is an area, how can it be negative? So at the beginning of this video, I mentioned that the integral is the signed area. So let me explain what I mean by signed area. On the interval from 1 to 4, let's see, 1 is here, 4 is here. So from 3 to 4, the graph is above the x-axis. And from 1 to 3, the graph is below the x-axis. What I mean by signed area is the following. If the function is above the x-axis, then the integral is simply going to be the area, the positive area. And if the graph of the function is below the x-axis, then the integral is going to be minus the area. That's why it's going to be negative in this case. That's all for this video, and I'll see you next time.